In my Structural Engineering Made Simple series, today I would like to talk about shear reinforcement design for concrete beams. Please take a moment and read the disclaimer at the bottom of this slide before we continue. Reinforced concrete sections are designed for longitudinal steel bars, for bending, and transverse reinforcement, in other words stirrups, for shear. This video explains the design for shear. In general, the process includes the design for stirrup shape, bar size and spacing, checking the pertinent code requirements, and the detailing for stirrups and their arrangement in the beam. These are pertinent references used in the preparation of this video. These figures show some stirrup design configuration. This one to the left shows a rectangular section with a closed loop stirrup. The one at the middle shows a rectangular section with open loop stirrup. And the one to the right shows a rectangular section with multiple stirrups. Please note that in seismic design and in cases where a section must also be designed for torsion, only closed loop stirrups are allowed. For T-sections, the dimensions are shown in this figure. Notice the BW, which is the width of the web of the T-section. This is called the effective width, and that is the one is used for shear calculations. Here are the notations. AS is the area of longitudinal tension steel. A sub V is the area of shear steel. It is the bar cross-sectional area multiplied by the number of stirrup legs. B and H are the section width and height. D is the distance showing the location of a steel measured from the center of tension steel to the extreme concrete compression fiber. It is also called the effective height of the cross-section. F prime sub C and FIV are the concrete compressive strength and shear steel yield strength in PSI. And steel with FIV of smaller than or equal to 60,000 PSI are often recommended for shear applications. MU is a factored applied moment at the location of the shear force V sub U. V sub C is the nominal shear resistance of the plain concrete section. Vs is a nominal shear resistance of the stirrup. Vn is a nominal shear resistance, which is the summation of Vs and Vc. And V sub U is a factored applied shear force. We also introduce phi as the resistance reduction factor, which is 0.75 for shear. And the steel ratio here we show it as rho W, which is AS divided by BWD. Location of critical section for shear. The factored shear force for design, V sub U, is computed at the critical section for shear. If the following conditions are satisfied, the critical location for maximum shear is at the distance d from the face of support, otherwise shear is computed at the face of support. The reaction in direction of applied shear produces compression at the end region of the beam. Loads are applied at or near the top surface of the beam. No concentrated load applies within D from face of the support. Generally, in the following, the shear is also computed at face of the support. In inverted T-beams, when there is a loading on the bottom flange, the support for the beam that is being analyzed is another beam of the same depth, and the support is subject to tension. If the beam is integrally built with the support, per ACI, it is acceptable to compute VU at the face of the support. Basic design equations. The total nominal shear resistance Vn is computed as follows. Vn is equal to V sub c plus Vs, in which V sub c is the shear resistance of concrete as we mentioned, and Vs is the shear resistance of shear reinforcement, in other words, stirrups. The shear resistance of concrete V sub c is computed using a simple equation, which we call it in this video as a short formula, or a more elaborate equation, we call it the long formula. Here are the equations. The short formula V sub c is 2 square root of prime sub c BWD. Long formula V sub c is 1.9 square root of prime sub c plus 2500 rho W, the quantity multiplied by VUD over MU, and then multiplied by BWD. There is an upper limit of 3.5 square root of prime sub c BWD. The bending moment Mu is at the section where Vu is computed, and the ratio VUD over Mu cannot exceed 1. There are other equations now in the code that you can refer to for other conditions. We multiply V sub c by parameter lambda equal to 0.75 if lightweight concrete is used. The V sub c equations are modified when an axial compression or tension are present. See ACI 2014 chapters 9 and 22 for these equations. For the common case of using vertical stirrups, Vs is obtained from the following equation. V sub s is AV times FYVD divided by S, where S is the spacing between the stirrups. AV is computed based on the stirrup configuration. For example, if a number 3 stirrup made of one single loop or a U shape is used, AV is equal to 2 times 0.11, which is 0.22 square inches, where 0.11 is the cross-sectional area of number 3 bar. If the stirrup group involves 3 legs, then AV would be 3 times 0.11, which is 0.33 square inches. Three conditions are possible in shear design. Number 1, if required nominal shear strength V sub n, which is Vu divided by phi, is less than V sub c over 2, no stirrups are needed. 2, if required Vn is larger than V sub c over 2, but is smaller than V sub c, minimum shear reinforcement is used per following equations. AV minimum is 0.75 square root of prime sub c divided by FYV, the quantity multiplied by BWS, and 50 divided by FYV, the quantity multiplied by BWS. The larger of the two is used as the AV minimum. 3. If required Vn is larger than V sub c, we need to design appropriate shear reinforcement based on the difference between Vn and V sub c. In other words, Vu divided by phi minus V sub c. Here are the limitations. The spacing S is limited to d divided by 2 and 24 inches if Vs, which is AV FI VD over S, is smaller than 4 square root of prime sub c BWD. And the limits are reduced. In other words, S is limited to d over 4 and 12 inches if V sub S is larger than 4 square root of prime sub c BWD. However, Vs cannot exceed 8 square root of prime sub c BWD in any condition. Furthermore, the value of square root of prime sub c cannot exceed 100 psi unless the minimum shear reinforcement is provided in the section. Step-by-step procedure for design. Step 1. Compute the applied shear force V sub u using applicable load combinations and structural analysis. For a simply supported beam of a span length L and a support width equal to W, and considering two conditions of A, dead load and live load on the entire span length of the beam, and B, dead load on the entire span length of the beam plus live load on L over 2, in other words, half of the beam, the following envelope for shear diagram may be used for computing V sub u, which is at the distance z from the center line of the support. Notice that the distance z is half of the width of the support plus d. This V sub u is computed at that distance z from this trapezoid. V1 is a shear force at the center line of the span, while V2 is a shear force at the center line of the support. If we take QD as a dead load and QL as a live load on the linear foot of the beam, then with 1.2 dead load and 1.6 live load factors, we can show that V1 is equal to 1.6 QL L over 8 and V2 is 1.2 QD plus 1.6 QL times L over 2. And then from the trapezoid, we can get V sub u as V1 plus the difference of V2 and V1 multiplied by L over 2 minus Z, and then quantity divided by L over 2. Please remember that this is only for simply supported beams. For cases other than a simply supported beam, a detailed structural analysis is needed to compute V sub u. If the structure is made up of at least two equal spans or almost equal spans under a uniform distributed load and with live load not greater than 3 times dead load, approximate values for V sub u can be used as follows, and these are per chapter 6 of ACI. V sub u is 1.15 QU ln divided by 2 for exterior face of the first interior support, and V sub u is QU ln divided by 2 for face of all other supports, where L sub n is a clear span as shown in that figure, and QU is 1.2 QD plus 1.6 QL. Step 2. Compute the required shear capacity is Vn equal to Vu divided by phi, taking phi equal to 0.75. Step 3. Compute V sub c. For a quick computation, use the short formula. V sub c is equal to 2 square root over prime sub CBWD. Now, if V sub n is smaller than V sub c divided by 2, no shear reinforcement is needed. However, if V sub n is larger than Vc over 2 and smaller than V sub c, the design stirrups are based on the minimum shear reinforcement required. To do this, first we decide on the stirrup configuration. Let's say a single loop we use, therefore AV is equal to 0.22 square inches with the number 3 stirrup. Then we use the smallest of the following four values for S. The first equation and second equations are based on the minimum amount of steel. The third and fourth equations are based on the limitations on S. If required Vn is larger than V sub c, then we need to design appropriate shear reinforcement based on the difference of Vn and V sub c. And in this case, after we decide on the stirrup configuration and A sub V, we pick up S as the smallest of the following five values. The first value is based on the equation for V sub S. The second and third equations are based on the minimum amount of steel. And the fourth and fifth equations are based on the limits on S. Step 4. Make sure Vs is less than the limiting value of 8 square root of prime sub CBWD. If Vs is smaller than 8 square root of prime sub CBWD, however, is larger than 4 square root of prime sub CBWD, then we need to reduce the spacing to no more than d over 4 and 12 inches. Step 5. Now provide the detail for the design. Use fractions of an inch for the spacing. For example, if the spacing S from the above procedure is equal to 8.29 inches with a number 3 bar, this is what your final design could be. Use number 3 at 8 and a quarter of an inch on centers. Other design considerations. For simplicity, the spacing designed based on the VU at D from the face of the support can be used throughout the span length of the beam. Away from the support, V sub U reduces, and as such the spacing S can be lengthened. This can be done at every 3 to 4 feet of the length of the beam, and then we change S to save steel. However, the extra labor involved in precisely implementing a variable S along the span length may not be a practical solution. That is why designers generally prefer to use the same S throughout the span length of the beam. In certain cases, bent top bars can also be used to provide additional shear strength, Vs, if necessary. What if situations? What if Vs exceeds 8 square root of prime sub BWD? This limit is provided as a way of preventing over-design for steel. If this happens, the cross-section size needs to be increased to obtain a larger V sub C and larger limit for Vs. What if the spacing from calculation is too small? To avoid this situation, one solution is to change the stirrup configuration to get a larger AV. For example, 2 loops can be used for the stirrup. Another solution is to compute VU away from the critical section and accommodate a longer S. This can be the case in areas close to the midspan for simply supported beams, for example. Let's look at an example. In this example, we would like to design stirrups for a simply supported beam of 30 feet in span carrying a live load of 1.373 kPa per linear foot and a dead load of 1.049 kPa per linear foot, and this excludes the self-weight of the beam. The beam size is 16 by 24 inches and the width of the support is 14 inches. Tension steel used is 2 number 11 plus 2 number 10. We will be using a prime sub C of 4,000 and FYV of 60,000 psi. We need to compute the self-weight of the beam, that is 16 by 24 divided by 144 to convert the area into square feet, then multiply by the density of concrete, which is 150 pounds per cubic foot. The answer is 400 pounds per linear foot. We add this to the existing dead load and we get a total dead load of 1.449 kPa per linear foot. Based on the longitudinal bars, we have 1.5 inches of protection cover, and if we use number 3 stirrups, the D would be equal to 21.42 inches. We compute V1 and V2 from previous equations to build up the envelope in computing V sub U, and the distance Z is half of the width of the support, which is 14 inches in this case, plus the distance D. 14 divided by 2 plus the distance D, we end up with 28.42 inches, and that is equal to 2.37 feet. Putting that in the equation, we come up with the V sub U equal to 51 kPa. Now we compare it with the capacity of the concrete section. Using the equation 2 square root of prime sub C BWD, we notice that the capacity is 43.4 kPa, and that means since the required VU divided by phi, in other words the required Vn, which is VU divided by phi, is 68 and is larger than V sub C, therefore we need to design the stirrups based on V sub S. V sub S, of course, is the difference of Vn and Vc, which is 24.6 kPa. That shows we have 24.6 kPa short of satisfying the required strength for this section. Using a single loop of number 3, we get AV equal to 0.22 square inches. Therefore, S from the 5 equations we mentioned before are computed. From the equation for Vs, we get 11.5 inches. From the two equations for minimum amount of steel, we get respectively 17.4 and 16.5 inches. And the limits are 10.7 and 24 inches. We pick up the smallest value, which is 10.7. Therefore, we offer our design as using a number 3 at 10 and 5/8 of an inch on centers. We also need to check Vs. Vs is equal to 24.6 kips, which is certainly less than 4 square root of prime sub CBWD, which is 86.8, and that means it is not exceeding 8 square root of prime sub CBWD. Therefore, the spacing we selected is okay. And here is a detail. Using long formula for computing V sub c. As an extra step, let's now find the value of V sub c using the long formula. We assume the two number 11 are extended to the end of the beam, while two number 10 are cut at some distance from the support, because this design apparently was done for the midspan, and we don't need all the 4 bars towards the end of the beam. Therefore, the total area of steel close to the support is 2 times 1.56. Each number 11 has 1.56 square inches of area. So we have a total steel area of 3.12 square inches. Therefore, rho W in that region is 3.12 divided by 16 by 21.42, which is 0.0091. In order to compute the term VUD over MU, we need the bending moment at the distance z from the center of the support. The factor total load using 1.2 and 1.6 load factors for dead load and live load respectively is 3.936 kips per foot. The equation for MU for a uniformly distributed load on a simply supported beam is the following. MU at the distance z is QU z times L minus z divided by 2. Plugging the numbers there, we come up with MU equal to 128.9 foot kips. Now we compute the ratio of VUD over MU, making sure that appropriate units are used. We ended up with 0.71 for that ratio, which is smaller than 1 because the limit is 1, therefore we use 0.71. In any case, if this ratio exceeds 1, we use 1. Plugging that in equation for V sub c, the long equation, we ended up with 46,719 pounds. It is smaller than the limiting value. Therefore, V sub c from this equation is 46.7 kips. We compare it with V sub c from short formula. You notice that there are some differences there. The bar arrangement designed in the example is for the maximum shear that happens close to the support. Closer to the midspan, the stirrup spacing can be lengthened to save on steel. However, because of the simplicity, often in practice the same spacing used throughout the span length of the beam. Thank you for watching this video.